Namaskar, I am Dr. Nisharani, Superintending Geologist from Photogeology and Remote Sensing Division, Geological Survey of India Training Institute, Hyderabad. My session is on interaction with atmosphere in remote sensing. During my session, I will discuss on scattering, about absorption, spectral response, and types of remote sensing. Interaction of electromagnetic radiation with the atmosphere is important in remote sensing as the sun is the primary source of electromagnetic radiation on the earth. As the energy passes through the atmosphere, it interacts with the molecules and particles present in the atmosphere. In the atmosphere, electromagnetic radiation is scattered or reflected and absorbed, and the remaining amount of energy passes through the atmosphere will reach to the Earth's surface. Here we can see energy from the sun started to reach on Earth's surface, but in between in the atmosphere, aerosol, clouds and molecules are present. Then this energy will interact with these molecules, aerosols and cloud, and some of the energy will be absorbed and some will be scattered. Scattering: when electromagnetic radiation passes through the atmosphere, interact with the suspended particles such as aerosols and clouds. Therefore, scattering process happens. It occurs when particles or large gas molecules present in the atmosphere interact with and causes the electromagnetic radiation to be redirected from its original path. Here we can see energy is redirected. There are basically three types of scattering which takes place. One is ray scattering, second is mist scattering, and third one is non-selective scattering. Relay or molecular scattering. It occurs when particles are very small compared to the wavelength of the radiation. Relay scattering is primarily caused by oxygen and nitrogen molecules. This causes shorter wavelengths of energy to be scattered much more than the longer wavelengths. This is a dominant scattering process in the upper atmosphere. Sky appears blue during the daytime because of this phenomena. Second is mass scattering or large particle scattering. It occurs when the particles are equal to or larger than the wavelengths of the radiation. Dust, pollen, smoke and water vapor are common causes for this scattering. Mass scattering influences longer radiation wavelength than the Rayleigh scattering. It occurs mostly in the lower portion of the atmosphere where larger particles are more abundant and dominates when cloud conditions are overcast. Cloud appears white because of the mass scattering. We can see here how mass scattering is happening and how clouds are interacting with the energy. Third is non-selective scattering. It occurs when the particles are much larger than the wavelength of the radiation. Water droplets and large dust particles can cause this type of scattering. All wavelengths are scattered about equally. This type of scattering causes fog and clouds to appear white to our eyes. Because blue, green and red colors scattered approximately in equal quantities, and because of that we are seeing white color of fogs and clouds. Since cloud scattered all wavelengths of light, this means cloud block most energy from reaching the Earth's surface. This can make interpreting and analyzing remote sensing data very difficult in areas prone to cloud and fog cover. Absorption is another important mechanism. It occurs when electromagnetic radiation interacts with the gas molecules, dust particles in the atmosphere. This phenomena causes molecules in the atmosphere to absorb energy at various wavelengths. Ozone, carbon dioxide and water vapor are the main atmospheric constituents which absorb radiation. These gases absorb electromagnetic energy in a very specific region of the spectrum. They influence the spectrum where we can look for remote sensing purposes, and the areas of the electromagnetic spectrum that are absorbed by the atmospheric gases such as water vapor, carbon dioxide and ozone are known as absorption bands. There are certain areas in electromagnetic spectrum where the atmosphere is transparent or no absorption of energy to a specific wavelength. Those regions where no absorption is happening is known as atmospheric windows. These windows allow the radiation to reach on the Earth's surface. Therefore, in these regions, remote sensing can be done. Here we can see entire wavelength spectrum, and these blue color are the regions where remote sensing can be done. Whereas these are the regions where all the energy is being absorbed by the atmospheric gases like ozone, water vapor, carbon dioxide, etc. So these regions we have as opaque region where remote sensing cannot be done. Quiz is there. First quiz is redirecting of radiation by atmospheric particles is, first option is backscattering, second option is reflectance, third option is scattering. Correct answer is option 3, scattering. We have another quiz. Area not influenced by the atmospheric absorption is known as option A, receiving zone, option 2, atmospheric window, option 3, transit zone. Correct answer is option 2, atmospheric window. Radiation target interaction is another important element in remote sensing. Radiation that is not absorbed or scattered in the atmosphere can reach the Earth's surface and interact with the target. When electromagnetic energy reaches the Earth's surface, there are three possible ways of energy interaction with the surface feature. First is absorption, second is transmission, and third is reflection. Absorption occurs when radiation is absorbed into a target. Transmission occurs when radiation passes through the target, and reflection occurs when radiation bounces off the target and is redirected. Here you can see energy is striking on the leaf, and once it's striking on the leaf, it will behave in a different way. If it bounces back, it is called reflection. If it is absorbed, then it is called absorption, and the energy passes through the leaf, then it is called transmission. In remote sensing, we are most interested in the measuring the radiation reflected from targets. There are two types of reflection: specular reflection and diffuse reflection. Specular reflection means when a surface is smooth or mirror-like surface. In this reflection, all the energy is directed away from the surface in a single direction. Second is diffuse or Lombardian reflection. This reflection occurs when the surface is rough and the energy is redirected or reflected almost uniformly in all directions. Here we can see it's a surface which is like mirror-like. The light which is striking on the surface, it's redirected in a single direction, and water surface behaves like mirror-like surface, and we can see here a rough surface is there. So energy is reflected almost uniformly in all the direction. There are some examples of reflection like water and green colors of leaf. Water appears blue because it absorbs energy in longer visual wavelength and near infrared region than the shorter visual wavelength. That's why water looks blue or blue-green due to the stronger reflectance at these shorter wavelengths. In leaf, chlorophylls are there, and these chlorophylls are strongly absorb radiation in red and blue, whereas it reflects green wavelengths. That's why we are able to see the green color of the vegetation. Another quiz: type of reflection when energy hits and reflects from a smooth surface known as Option 1 specular, option 2 diffuse, option 3 angular. Which one is the correct answer? Correct answer is option 1 specular. Another quiz. Which among the following is a scattering process? Option 1 valence, option 2 me, option 3 diffuse. And correct answer is option 2 me scattering. Spectral response. Different surface features reflect and absorb the sun's electromagnetic radiation in different ways. The reflectance properties of an object depend on the material, its physical and chemical state, the surface roughness, as well as the angle of the sunlight. The reflectance of a material also varies with the wavelength of the electromagnetic energy. The amount of reflectance from a surface can be measured as a function of wavelength, that is known as spectral reflectance or spectral curve, and sometimes spectral signature. Every object on the Earth's surface have characteristic absorption feature at certain wavelength, and based on these spectral absorptions, individual objects on the Earth's surface can be identified. Here we have a spectral signature of two different object or target. These are for the minerals, these are for the soils. Here minerals are showing different absorption points, and accordingly we can identify them. Here soils are showing different absorption features. These are the absorption features, and we can identify different soils. Broadly, remote sensing can be divided into two: optical remote sensing and microwave remote sensing. Here we can see we have entire wavelength spectrum, and from visible to infrared region is known for optical remote sensing, and this part is known for the microwave remote sensing. Multispectral and hyperspectral remote sensing is a part of optical remote sensing, and it ranges from 300 nanometer to 3000 nanometer. These regions are very useful for mineral exploration, lithological and structural mapping, alteration zone mapping. Thermal remote sensing ranges from 3000 to 5000 nanometer and 8000 nanometer to 14000 nanometer. This region is very useful for fire detection, surface temperature measurement, and thermal pollution studies. Microwave remote sensing ranges from 1 millimeter to 1 meter, and this region is very useful for the tectonic studies, surface upliftment, subsidence, and active fault zone mapping. Data sets in practice: Resource Set 1, Landsat 8 OLI, Landsat 7 ETM. Ester data is the example of multispectral remote sensing. Averis NG, Hyperion is the example of hyperspectral remote sensing. Thermal bands of multispectral data is the example of thermal. ALOS pulsar, SAR, radar, DEMS data is the example of microwave remote sensing. Thank you. This is the end of the current session, and next session will be on the sensors and data products.